be talking about cavitation. Not only cavitation, but several different ways that we can mitigate against cavity forming, because cavitation is an undesirable aspect of transient phenomenon, and we would like to eliminate that as far as possible. Where we cannot eliminate it, we would like to keep it under control so that the pipework doesn't get damaged. But the ideal is to eliminate cavitation altogether. Here, cavitation is likely when the pressure goes below the vapor pressure. We all know that, because if you do a flash calculation, the liquid will vaporize if the pressure goes below the vapor pressure, and that is what PIPENET uses to predict cavitation. Just the same way as flow sheeting programs or process simulation programs do the same sort of thing. And there are 4 options in PIPENET. No cavitation. You may wonder, why do we have the option no cavitation? Because no cavitation actually is not a trivial option. There are useful information that you can derive with the no cavitation option in order to eliminate cavitation. And we will look at some of those cases today, some very simple cases. And vapor cavitation is the classical textbook method. And the classical textbook method is from a book called Fluid Transients by Wiley and Streeter. That is generally regarded as the classic textbook for transient analysis in pipe networks. And this model is from that textbook and is the classical model. Channel cavitation is our own proprietary model. We will see why there are inadequacies in the vapor cavitation model in a number of situations. It's a very, very useful model, and that's something that is adequate for many cases. However, our own proprietary model called the channel cavitation model is something that is a must in certain cases. And it's a unique model. We developed it ourselves. The discrete gas cavity model, again, is basically from the classical textbook by Wiley and Streeter. It's because many systems have a small amount of gas or gas pockets in the liquid. And the important thing about the difference between gas and vapor, as you all know, the definition is a vapor can condense if you increase the pressure, whereas gas doesn't condense if you increase the pressure. That's a definition of the difference between vapor and gas. So if there is a gas pocket, even if it's very small, present in the liquid, it can act as a cushion and reduce the pressure surge. But you must not use this as an excuse to reduce the pressure surge. You must be able to justify using this model, but that is up to you as an engineer. We cannot make a recommendation because it depends on your system and whether there is even a small amount of gas present or not. So these are the 4 options in PIPENET. So no cavitation option. Let's look at the options in a little bit more detail. is very fast. You can understand that because it is the simplest model. It solves the basic equation and is a stable numerical solution. All the options in PIPENET are stable, but numerically, it's very simple. That's what it means. And it's a textbook model. The disadvantages, the main one, of course, that it allows the pressure to go below the vapor pressure, or sometimes even absolute zero pressure, which is totally unrealistic in real engineering terms. But as I said, you can use the no cavitation option under certain circumstances to alleviate cavity forming. And it cannot predict pressure surge due to cavity collapse. It's obvious, because if the cavity, you do not allow cavity to form, you cannot model cavity collapse. And that is often a source of pressure surge. And hence, that if you have a cavity and you're interested in predicting the pressure surge when the cavity collapses, then quantify it, then it is not of much use. Vapor cavitation is the fastest cavitation model. Stable numerical solution is a textbook model. So if you use the vapor cavitation model, you can always refer back to the Wiley and Streeter textbook and say the model is from there. But as I said earlier, it has certain inadequacies, and you cannot always use it for realistic engineering solutions. The main disadvantage, it ignores the effect of the void fraction, which may lead to indefinitely growing vapor volumes. And when Wiley and Streeter wrote the book, it was hard enough to model small vapor pockets, and that model was good enough for that purpose. But in reality, you can actually get significantly big void volumes and fraction, and it is not good in such cases. It cannot predict the cavity configuration and distribution in pipes, because often when cavity forms, you get a continuous pocket of vapor rather than small bubbles which are distributed in the liquid. And it cannot model such a case. Applications. It is, as I said, is a very useful model, provided you keep this point in mind, that you cannot always use that for all cases. So it's a good tool for relatively, the advantages are here. So it's a good tool for relatively small cavities, but the volume occupied by the cavity does not affect the behavior of the system. The model can give accurate results if the cavity is large or small, occur in horizontal or gently inclined pipes. Okay, and whereas, of course, if it's a small pocket of cavity, then you can use it in most cases, because the static head is not affected by the cavity. And that's a key point. The Wiley and Streeter model does not consider the static head effect. And that's why we have this limitation. But if it's a very small cavity, it's good enough in most cases. So it looks like this. Small pockets of vapor, not gas, it's vapor, distributed throughout the pipe. But of course, the void fraction actually will change, and PIPENET does model that. PIPENET doesn't assume that the void fraction is the same throughout the pipe. You cannot assume that. For example, if there's a valve here and the valve closes, you will have a larger void fraction in this part of the system than down here. And PIPENET does model that. And when you actually plot the graphs, you can plot the graphs of the cavity volume in different parts of this pipe. Okay, that's a beautiful model in PIPENET. Channel cavitation, as I said, it is our own model. It provides more accurate simulation in case of large cavity volume. Okay, and the static head effects are considered, because if you have a large cavity volume and the pipe is inclined, then the vapor phase will be separated from the liquid phase. And so we need to consider the static head effect. And that's one of the key differences with the cavitation model. It can predict the cavity configuration. What this means is that the cavity will be separated from the liquid, and it can model the length of the cavity and the cavity volume and things like that. And the most important thing is this cavity size will not grow indefinitely. We'll have a look at an example very, very soon where we can see the difference. The disadvantage, slower calculation. It's not slow. PIPENET is a very fast program, but it's slower than vapor cavity model. It cannot be used with milepost pipes. Milepost pipes is where you have one pipe where you can actually input the variation of the elevation in the form of a table. If you have that, then you cannot use channel cavitation. Application where you have large cavities, especially in vertical or steeply inclined pipes. We already seen this. It can predict the length of the cavity, take into account the static head, and so on. And it looks like this. You have a vapor cavity which is separated from the liquid. And we often have such a situation. And the discrete gas cavity model, again, is from the Streeter textbook. Table numerical algorithm, because it's a textbook model, and reduces the pressure surge if a gas pocket is present. It can make the calculation slower, but don't forget that in saying that there is a gas pocket, it's not for two-phase flow. So it cannot be used for stratified flow and things like that. The gas pocket is in one place essentially, or it's in the form of a bubble that can move. It's not a two-phase flow situation. That is basically the four models for cavitation in PIPENET. Let's carry on. Let's look at the no cavitation option. I said that the no cavitation option has its uses. Why? Because we started with the premise that our aim is to eliminate cavity formation if possible. If we can do that without modeling cavity formation, it makes our life easier. In other words, if we can eliminate cavity formation without modeling a cavity, that makes our job easier. So I'm going to consider 3 cases where we show that the pressure actually is below absolute 0 here, which of course is unrealistic, but we can quantify the level by which the pressure goes below the absolute 0 pressure. And then we can try and do something about it. Okay, so let's go. It's the basic model. By the way, this is based on a real model. It's real pipe work, but it's sort of cut down to make it very, very simple. The real model is much more complex than this. What we're considering here that pump tripping at 20 seconds. It's a variable speed pump with a control system that sets the initial speed, but at 20 seconds, there's power failure and the pump loses power. That's what we are considering. It's the same with that pump. So there is a total power failure. And of course, when there is total power failure, the control system is ineffective because the control system can only work if the pump has power. So that is what we are modeling here. Because there are other control systems and receiving vessel and things like that. Let's see what happens. Don't forget that we've chosen the no cavitation option here. It's a non-trivial model because of the presence of the control system, but you can see that even with a non-trivial model, it's running actually quite fast. I can show the minimum pressure. I need to refresh it. So you can see that the pressure goes below absolute 0. You see the units is bar gauge. The absolute 0, of course, is -1 bar gauge. It is going below that. You see, and the beauty of this, it quantifies the extent to which it's going below the absolute 0. Now, what we would ideally like to have is to bring this back to around 0 bar gauge. And one thing we could do to increase the pressure to 2 bar. See, we could install a tank here, for example, which has an normal elevation of 20 meters or something like that. and that will increase the pressure here. Now, please remember that that is not going to increase the pressure here by 2 bar. Because what will happen when you increase the pressure here, the flow rate through the system will also increase. And when it increases, the pressure surge, or the vacuum here, you can expect it to be such that it will not increase the pressure by 2 bar. It will increase by less than 2 bar. Here again, it's the same criteria we're considering. The 2 pumps are tripping because there's no power to the pumps. And I did this in front of your eyes. I increase the pressure here to 2 bar. The model remains the same. But you can see now it's slightly below atmospheric pressure. It did not increase by 2 bar. It increased by, I believe, 1.8 bar or something like that. I explained the reason. The reason is that the initial flow rate is higher. So when this is a turbopump model that's used, the vacuum pressure that you create because of the higher flow rate will be more. That is why it doesn't go to increase by 2 bar. So you see, we didn't model cavitation here. We found a simple way of solving this problem. So that's what engineering is about. If possible, use the simplest way to solve the problem. I'm not saying, by the way, that this is a practical proposition, because I'm not. There may be cases, many cases, you cannot do this. I'm not saying, please increase the inlet pressure to 2 bar. I'm just saying that if you have the option, this is a methodology you can use to find out how much you need to increase the pressure in order to eliminate cavity formation. And of course, an alternative would be to put this back to 0. Back to 0. See, this has a height of 50. I can increase that to 20, let's say. This model is called the receiving vessel because there are very large cooling water systems, which use seawater, and you wouldn't dump the water straight into the sea. There would say what's called a receiving tank. I don't want to go into the details of why you have the receiving tank and so on. Basically, just to stop air flowing back into the system. And we can increase the size of that receiving tank, and that will create a back pressure, bigger back pressure through the system, and we hope that would be enough to overcome the absolute 0 pressure, and indeed to increase the pressure above the vapor pressure. You see, we're increasing the pressure, the height from 5 bar to 20 bar. So we're increasing the elevation back pressure by 15 bar, which is approximately 1.5 bar increase. That's the reasoning behind increasing it to 20. That's quantified by the level of the pressure that we were getting here. See, it's above absolute 0. It's also above the vapor pressure. So there is cavitation that's eliminated here, minus 0.95. That's bigger than that, so we will not have cavity forming in the system. So we've eliminated cavity. So this actually is, so don't dismiss the no cavitation model. If you have very large systems, it'll run faster, and it may not be necessary for you to model the cavity forming. And that is the beauty of the new cavitation option. So let's press on and to compare the other three models. Let's compare the vapor cavitation, channel cavitation, and the discrete gas cavity model in a horizontal pipe. See, what we said was if the cavity volume is small and it's a horizontal pipe, the vapor cavitation model, which is a much simpler model and a textbook model, would be as good as the channel cavitation model. On the other hand, the discrete gas cavity model is quite a different model because it's not about modeling cavity, but it's about modeling the effect of the presence of a gas as opposed to a vapor. So this is what we're modeling, and we will look at the results in the form of a table in just one moment. So let's see, these are the three models. Vapor cavitation, module options. You can see that we've selected vapor cavitation here, and the pressure here is 6 bar gauge, and the pressure there is 0. That valve closes in 1 second, and that valve remains open. So we can expect a cavity to form somewhere here. A cavity doesn't necessarily form here. You know, when this valve closes, you will create a vacuum pressure here that can go below the vapor pressure. By the way, you can see what actually the diagram, what that actually is showing. So that's the pipe length, and that is the pipe elevation. So you can see it's a horizontal pipe. We can look at the tabular result. The tabular result is quite useful, and you should look at it. See, it's 12.0059, and that is the vapor pressure of water. They're on both on pipe 1, as we expected. So it's at this position here. That's pipe 1. So let's keep that in mind. Change to channel cavitation. That's all the change I've made. If you remember, the maximum pressure is just over 12 bar. See, it's virtually the same. You must expect some difference. It's of the order of 0.006% or something like that, which is in engineering terms is completely acceptable when you consider that the models are completely different models. Let's then use discrete gas cavity model. It's got the void fraction, some default value, and this is the pressure. What this means is that at that pressure, the gas will have that void fraction. Because the pipe pressure within the pipe will be higher than that, and hence the void fraction during operation will be less than that. So you can see that the air pocket, even though it's very, very small, it actually makes a significant difference to the maximum pressure. But as I say, you must not use this as a tool for reducing the pressure surge, unless, of course, you deliberately introduce a gas pocket into the system. That is not a desirable thing to do, but if there was a gas pocket present, it can reduce the pressure surge. Okay. So you can see that there is a significant decrease in the maximum pressure. So if we look at the table of comparison, you see the vapor cavitation and channeled cavitation give virtually the same pressure surge, maximum pressure and the minimum pressure. Whereas the discrete gas cavity model gives a smaller maximum pressure, and also it doesn't go as low as the vapor pressure. Okay, with these two, there is cavity forming. With this one, when there's a small amount of gas present, the pressure oscillations are reduced, or the amplitude of the oscillations are reduced to such an extent that it doesn't even go below the vapor pressure. Let's see what happens if we compare the three models in a pipe with an apex. So it goes up and then down. Now, this is 30 meters. In the diagram, I showed 15, but it's 30 meters elevation difference. And the inlet pressure is 3 bar gauge. This is just to, show the difference. So I've exaggerated it a little bit. Vapor cavitation only. That valve is closing. That remains open as before. The cavity forms in the same position. The maximum pressure is 12.36 bar gauge. Let's switch to channel cavitation. Do the same thing. I've not changed anything else. It's about 10.4. So it's a little bit less than the previous model, the vapor cavitation. Discrete gas cavitation, discrete cavity model. It's, let me just, sorry, I think that, let's make the cavity slightly bigger. So then you can see the effect of the size of the vapor gas pocket, that when the void fraction was 0.001, it made virtually no difference. But if I increase the amount of gas to 0.01 void fraction, then it made a significant difference to the maximum pressure. So you can see the effect of the different models. Now let's go take one step back and see what's actually happening. I said to you that one of the weaknesses in the vapor cavitation model is that it ignores the size of the cavity as far as the static head is concerned. For example, if this pipe is partially full, when you consider vapor cavitation, it doesn't consider the static head effect of the vapor pocket. Because it's clear, the pressure is 0, and when the valve closes, what can we expect to happen? That we will have a vapor pocket forming here, and the vapor pocket will come down to a level where the static head makes the pressure here more or less equal to the vapor pressure. See, that's how far the liquid column will go down. I repeat, the liquid column will go down to such an extent that because this valve is open, the static head must create a pressure here, or static head loss will create a pressure here, which will be approximately equal to the vapor pressure. See, in the vapor cavitation model, we are ignoring that. Whereas in the channel cavitation model, we are taking that into account. So let's see. See, if we're not taking that static head effect into account, what can we expect? We can expect the flow to be continuous. In other words, the vapor volume to increase indefinitely. That is a problem. Let's show the pipe labels again. It's pipe 2. Pipe 2, cavity volume at the inlet of that pipe. So look, is growing indefinitely. In fact, it can become bigger than the volume of the pipe. See, that's nothing to do with PIPENET. It's the model that comes from the textbook model that comes from Wiley and Streeter. And, you know, it's a textbook model, and it's a highly respected model, and it's very, very useful. But in this case, it's unrealistic because the cavity volume keeps increasing indefinitely. Let's switch to the channel cavitation model. Don't forget, the primary difference is it models the actual cavity and the static head effect of the fact that this pipe is partially full. And that is our own model. So let's go to the same pipe in the same position, because the channel cavitation, you see, it's not simply a matter of calculating the cavity volume, because we can go but do better than that. We can actually determine the length of the cavity. You can see that the cavity increases and it stays at a steady state level. It doesn't grow indefinitely. And that is the beauty of the channel cavitation model. It assumes that there is a limit to how far the cavity size will increase. And that is the channel cavitation model. Let's go to same void fraction. We've already seen this result, and that is unchanged. Okay, so this is the difference between the 4 cavitation models in PIPENET. So that is the background. Now let's carry on and see how we can actually use PIPENET to alleviate the problem created by cavity forming. Cavity formation is undesirable. Let's look at some practical examples. So this is a 5-watt system from an FPSO. The first case we consider is without vacuum breakers. In other words, the system is built as it is to put out the fire with no consideration of the dynamic phenomenon that takes place and the possibility of cavity forming. Let's open that model. So it's the elimination of cavity by using vacuum breakers. That's what this is. Using vacuum breakers is a standard method for eliminating cavities. And this is a fire protection system. And this is where the aft pumps are located. And that is where the forward pump is located. So let's calculate and see. See, this will take a significant length of time because there are various control systems here. See, this is closed because it's got the dot in it. See, it's a form monitor. With this, I believe, is a deluge system, which is modeled as a nozzle. And there is a complex control system because this is an elastomeric valve, and this is a real system, and it's a beautiful model. See, that is the switch. That's called a signal selector. There's another signal selector here. And then the actual controller. That's the PID controller, which models the elastomeric operation of the elastomeric valve. So you can see that, this is the reason why it runs not terribly slowly, but slow in comparison to the models we've seen before, because of all these control systems and so on. So let's go to it's 75 bar. In reality, we may not get actually 75 bar gauge, but the point is it'll be a very high pressure. It may not be that pressure there because the pipe, for example, has gaskets and so on, which will absorb some of the pressure. And so we may not actually get exactly that pressure as the peak pressure, but it's no doubt that the pressure is very, very high. By the way, let's look at this tabular output. See, there are different pipe schedules which have been used in this fire protection system. And the reason why it produces this table is that the global maximum pressure of that 75 we looked at earlier on may not be the worst case. There may be a weaker pipe somewhere else in the system which has a pressure less than 75, but which exceeds the allowable pressure for that pipe schedule. And that is why it has this table. It's particularly useful if you have several different pipe types in your system. If you want to be even more particular, you can have a look at the next table, because for each pipe schedule, for each pipe size, it gives the maximum and the minimum, indeed the minimum pressure. So if you've got, you see the maximum allowable pressure, strictly speaking, although we talk about the maximum allowable pressure of the system, in fact, it actually depends on the pipe schedule, not only that, and also the pipe size. If you want to go to that detail, then you must look at this table. And it carries on. The maximum minimum pressure for all the pipes, and all the other items for the pumps, and so on. You see, the inlet and the outlet for these items. So do have a look at this table here. So PIPENET Transient module is not only about graphs. It's got very, very useful tables here. Anyway, we looked at this one, 75. That's on pipe 11 at the outlet. We want to see where it is. So I'm teaching you some tricks. Pipe 11, where is pipe 11? See, it takes me straight to the pipe 11. I don't have to do all kinds of searches and things like that. PIPENET does the hard work for you. So this is pipe 11. That's where the problem is. So if we have a look at pipe 11, is at the outlet of pipe 11. 11 is here. The pressure, it goes above that. Okay. So what are we going to do? One classical solution with fire protection systems is to use vacuum breakers. Let's look at the same pipe. Pipe 11. Same pipe. See, we've added the vacuum breaker here. The beauty of this, you already know this, I think, that the vacuum breaker allows air to come in. It's a little bit like the discrete gas cavity model in the sense that there is an air pocket that we artificially create here in order to reduce the pressure surge, except that this controls the air pocket. It allows air pocket to form if the pressure goes below atmospheric pressure. It allows air to escape if the pressure here goes above atmospheric pressure. And if it is defined in this way. It's in inches. This is what's called the CD of the valve. If this is 1, it means that it's a perfectly efficient valve. Set pressure is 0. In other words, if the pressure inside the pipe drops below 0, it'll allow air to go in. And the air going out, the valve that allows the air to go out is smaller, you can see. Why? Because if there is a chance of the pressure here going below atmospheric pressure, you want air to come in quickly, but when the system repressurizes, you want air to go out slowly, because otherwise there'll be a big bang. If the air goes out very quickly, and the water will follow that, and the water will stop flowing, and all the air is expelled. So that's why this valve, the air outlet valve, needs to be smaller in size. One of the important things to recognize with FPSO, I know that many of you are from Asia Pacific, and although this is for Europe, at least some of you are from Asia Pacific and India. And one point I'd like to make is that if you have an offshore platform, usually there is one high point, so it's sufficient to install one vacuum breaker in the system. With an FPSO, typically there are several vacuum breakers. These are all hydrants. There are several from high points, you can see. So installing one vacuum breaker and one high point is not enough. In this system, see, there are 13 vacuum breakers, and they're all identical. Okay, so let me do the calculation now. See, this system model is actually quite a complex model because there are a lot of control loops here. Control loops are difficult the model. And these run pretty quickly. So pipe 75, the maximum pressure is down to just about 19 bar, which is adequate in most cases. And as I said, if you want to check things out more carefully, you can look at this table, and that will show you the maximum pressure for all the pipe schedules. And you must make sure that these are below the maximum allowable pressure for each of those pipe schedules. So this is a classic solution for fire protection systems. See this, we looked at all of those things here. Cavity volume in pipe 1 is 0. So the pressure goes, in fact, if you look at the pressure very, very carefully, you'll see that it's slightly below atmospheric pressure. Doesn't matter which vacuum breaker you choose. See, it's slightly below atmospheric pressure. The first number, if you hover, you'll get two numbers. The first one is the time, and the second is the value. And we've got the inlet pressure. You can see that it's slightly below atmospheric pressure. Because why? Because that valve will have some loss. The air inlet valve or the vacuum breaker valve will have a small loss, and that gives the slightly negative pressure in the system. So let's go to the next application. That is about elimination of cavitation by using elastomeric valves. And here again, we consider an offshore platform here. Fire protection system on an offshore platform. By the way, you know, more than half the applications these days are for process applications. So do remember that the transient module is not only for fire protection systems, it's used very widely for process applications. PIPENET Transient module is not a competitor to programs like PipeSyn, Olga, and so on, because they have two-phase situations in steady state and dynamic, whereas we consider primarily single phase. The only two-phase aspect we consider is cavity. And PIPENET can model the movement of cavity. Don't forget, this is Dr. Chen can explain this a bit more. PIPENET actually can model the movement of a cavity within the system. But what it cannot model is two-phase flow. The cavity moving is different from two-phase flow. Okay, so we've got the elastomeric model. Before we do this, let me do it in a sequence, which is what I would like to show. It's the traditional conventional valve. They're called clap valves. The deluge valve only has two positions. It's fully open or fully closed. It does not control the flow rate. And we've got the deluge system explicitly modeled here. So let's go to PIPENET. So this is a traditional deluge valve. It's the model we were looking at. And some of you are already using dry pipes to model the discharge time, but there is no reason why you cannot always use or input the deluge system explicitly. And indeed, the way I actually built this model was to copy and paste a subnetwork of the deluge system. I only had the model of the ring main and the deluge system, and they were separate. And as we saw in the earlier webinars, you can actually combine networks, and that's how I modeled that. In fact, I'll show you how I actually did it. Sorry, I won't copy and paste the model. That'll take too long. Treat the selected pipes as dry. See, what I actually did was to copy the steady state model from the Spread-Sprinkler module and pasted it here, connected it here, and then use this option to make it dry. So that's what I did. And if you click on this pipe, of course it becomes red. And you can see that it's the initial state, because when the deluge valve opens, of course, it'll get flooded. So it's the initial state is dry. So all the pipes here are dry. You can see it more clearly if I do that, because this hash symbol indicates that it's a dry pipe. So this whole system is dry. It's a very conventional fire protection system on an offshore platform. The pump starts at 1 second, takes 10 seconds to run up. There's a caisson, which is partially full, and that gets full as the pump runs up. And there's an overboard dump valve, which is initially open. Then it closes in 5 seconds. And then the water comes through. The problem with a system like this, if you look at the elevation, and this is a problem that people had consistently with older systems. See, the elevation here is 15. When you open this valve, the pressure in the system is 0 because it's an open system. And if the valve opens, let's leave that elevation there. It opens at 1 second when the fire is detected. See, this elevation difference is 15 meters. So the pressure here will collapse to almost atmospheric, because the pressure here is atmospheric and this valve is open. And this will create a cavity here. And that's a problem with the system. When the pump repressurizes the system, that cavity will collapse and we'll get a high pressure. That's a problem here. So we're particularly interested in what happens in the high points in the system, because that's where the cavity is going to form. It's 68 and it's on pipe 12 at the outlet, which is here, which is what you would expect. Because the cavity forms here throughout this part, and that's the last bit to collapse. And you will get the maximum flow rate when that cavity collapses, and that's the problem. Let's look at the pressure there graphically. See, we saw 68 in the tabular value. I'm showing this because sometimes people are puzzled about why this pressure here is less than the maximum pressure we got earlier in the PIPENET tabular output. See, we get 68 there, but the graph doesn't show that. It's showing 23. So you can even use the magnifying glass. See, there's this magnifying glass, so you can examine things more closely, because if you got rapid vibrations, you can do that. You can also, I'm just showing you all these things because you find them useful when you're actually using PIPENET. You can zoom in this way. You can do that. Or you can also zoom in for doing that. Then, of course, you can put all kinds of things. You can put arrows and text. Whatever, you can do all that. But the point here is that this pressure is less than the pressure we got in the table. What's the reason for that? You see, we're doing the calculation with a time step of 0.03. See here, for the graphical output, we're using 0.1. So let's something called the smart output. Let's switch that on and see what happens. So I'd like trying to teach you features in PIPENET, not only about cavitation, but other things that you may find useful. So that's why I'm talking about this. See? So what's smart output mean? Let's leave that aside for a moment. See, we put the graphical output at 0.1 second. So there'll be 300 points on the graph. If you've made that 0.03, we'll have approximately 900 points. It'll take it slower to plot. Where smart output is very clever. What it does is to keep track of the maximum and the minimum value for that variable. So although it's plotting the graph with that resolution, it keeps track of the maximum and minimum. That's why it could tell that the maximum pressure, I think it's already got one open. So let's, here we go. That's why it was able to output that. So that is the purpose of smart output. What you can also do, of course, do that. See, it's running very fast when you consider what happens, because all these pipes are dry, so they'll get filled up one by one. We saw this in an earlier seminar, last seminar, in fact, about dry pipes. But I don't want to focus on that. I want to focus on the formation of cavities. See? Now, of course, it's done that because I plotted 900 points along the graph. And so if the graph shows a pressure that's less than what the tabular value shows, then it's because the time step is different. So you have the choice of using smart output or reduce the time step. Anyway, that's not the main point. The main point here is this, that we want to introduce the elastomeric deluge valve. Those of you who are working in the offshore industry will know that elastomeric deluge valves are being used more and more commonly. Let's make this. Oops. That's the easiest. Double check that the time step for calculation is the same. I'll start the calculation and then describe what it is. The fire is detected at 1 second. It's an automatic control valve, albeit not, it's not a PCV, it's a kind of self-controlling valve. And of course, it stays closed until the fire is detected. And you can see that the fire pump starts at 1 second. So we're assuming that the fire is detected at 1 second. So in the first 1 second, the system is in its quiescent state. Quiescent means it's just standing still, nothing is going on in the system. We also set the elastomeric valve in such a way that it cannot open unless the inlet pressure is more than 2 bar gauge. Okay, so what it means, you see, these elastomeric valves can be set in many different ways. And we are assuming in this case that it is set so that if the pressure is below 2 bar gauge, it remains closed. Okay, how do we do this? Let's look at the signal selector. The signal selector has got 2 input nodes, 60 and 70. See, this is what's called a minimum type. So it will choose the signal which has the lower value of these 2. The valve remains closed if the inlet pressure is 0. So how were these 2 conditions implemented? First of all, that is 0. And the signal selector here is of the switch type. And it switches from node 39 to node 59 at 1 second. Let me just zoom in a little. I hope you can see the node numbers now. See, that's 39 and that's 59. So it switches from node 39 to node 59 at 1 second. Now, because this value here is 0, the output of that will be 0 until 1 second. So this condition is implemented by this signal selector and the specification here that the time function has a constant value of 0. And here, that's a pressure sensor. And that's a switch. And the switch is on above 2 bar and off below 2 bar. So unless the pressure here is 2 bar or more, the output from here will be 0. So if one of these two conditions is not satisfied, the signal here will be 0. And don't forget, the output from a PID controller, in reality, it's 4 to 20 milliamps. That's the standard. But in PIPENET terms, the output is between 0 and 1. So this cannot be, the minimum value it can have is 0. But depending on the pressure here, that can have a value more than 0. That selects the lesser of them. So if the signal here is 0, that will set the valve position to 0. But if it's more than 1 second and the pressure here is 2 bar or more, that will switch to 1. And as we know, the output of this PID controller, which is based on the pressure here, can only be between 0 and 1. So this chooses lesser of the two values. So when these two conditions are satisfied, the value is 1, the value here will be less than 1. So the valve is controlled in that way. That is how we model elastomeric valve. If you set your model to work differently, then you have to use a different system for modeling this. Okay, so that's how you model an elastomeric valve. So let's have a look to see it's come right down to 68 or something like that before. It's 18 now. We can look at what's happening in that pipe 12. So the cavity volume status as 0. Okay, so that is how the system works. Okay, so it's not, there is a little bit of cavity forming here, but it's not very big, and it certainly doesn't collapse. When the small cavity collapses, so you can see that there is a very small spike in the pressure. So we've solved the problem by introducing the elastomeric valve. Of course, the classical solution is to install vacuum breakers, and most people, even if they use the elastomeric valve to stop the pressure surge due to cavity, they will still install a vacuum breaker as a backup. So this is about using elastomeric valve to reduce the problem due to cavity formation. Now let's go to the next example. Now we're beginning to talk about more process type of applications. See here, that's an LNG loading system, and the east berth is operating and the west berth is shut down. And these are the shutdown valves, and these are the downstream piping system, and that's, as you can see, that's the loading arm. And you've got the feed pumps here, and the bypass and so on. The important here, the simulation we're considering here is what happens downstream of this. We also need to consider what happens upstream, but that is not what I'm going to be looking at right now. I'm looking at the cavity forming downstream of these shut-off valves. Okay, let's go to it's an LNG loading system. And I always admire the system because, in my opinion, it's a beautifully designed system from a surge point of view. Click on that. See that valve starts to close at 5 seconds and closes in 15 seconds linearly. It's the same. One, as you know, is valve open, 0 means is fully closed. It's 25 seconds, so it's slower to close, but that valve also closes. That closes. You see, the best engineering solutions are simple because they work, and we all know that. You know, so the simple point here is that they made sure that this connection is at the base of the tank. And I believe, in fact, in many cases, this valve is actually inside the tank, storage tank, or on the tanker, LNG tanker. And because it's at the base of the tank, it has a static head, which gives that pressure. This is very, very simple points. So this valve's also closing. They're closing. As I say, I'm not going to pay much attention to what's happening here. It's only the loading system that we're considering, the loading arm and so on. So let's run the calculation. See, this means that there is cavitation. You see, this is what we saw earlier, because we're using the channel cavitation model. That is actually quite a difficult model, and that's why it slows down a little bit when there is cavitation. So let's look at that loading arm. That's a label for that loading arm. That's that loading arm. And also there's a valve here. And you know, it's not really that important, but we're more interested in what happens on the loading arm, because that's a weak point in the system. We need to avoid cavity formation here. So these are the 2 points we consider. If you're interested, we can also look to see what's happening in these 2 points. It's the same one, but with in was the, you know, the loading arm that's leading to the peak. Okay, let's have a look. That's the downcomer, because it's the channel cavitation. Wow, brilliant. See, there's no cavity. The cavity length is 0. And let's see, for good measure, let's look at the other loading arm that's working. That is also 0. By the way, there's another feature of PIPENET here at the graph viewer. You can share the axis, so they're both on the same axis. Sometimes that's very useful. You see, there's no cavitation. You can look at all these things, I mean, if you like. You can look at the maximum pressure. It's really actually not that useful because I don't think that's in the loading arm pipe 42. See, that's here. That's before the valve, which is the, you know, the traditional pressure surge due to valve closure. When the valve, that valve and that valve closes, the maximum pressure is about 22 bar, which I presume is acceptable in a design like this. So that maximum and minimum pressure actually are not of that much significance here. So let's consider an alternative way of designing the system. You install the system with no consideration of cavitation, and you know, you'd think cavitation is for boys. Why worry about it? So what you're doing, see that valve? This is not the case I want to consider. Sorry, I didn't open this. It's the same network. That valve and that valve are closing. That valve is constantly open. That valve is also constantly open. By the way, as I said, only one berth is working. See, it's 0. That means that that valve remains closed. That valve also remains closed. So, and this is connected somewhere at the top end of the tank. So, see what happens. The second part of the study would be this part. You know, is potentially there could be cavitation on this side as well. That's not something I'm considering. I'm considering the weakest part of the system, which is the loading arm. Okay, let's look at if there is cavity forming in the loading arm. Whoa. See, look at this. This is the length of the cavity. It's the length of the cavity along the pipe, 30 meters, down to 6.2. So the swing is almost 24 meters. So the cavity length is changing along the pipe by 24 meters. And that is huge. And that keeps oscillating, in fact, 23 and 6. So it's actually about, 17 meters swinging. So it is actually a big, big problem, the cavity forming and oscillating. Okay, so this is the length of the cavity downstream of the downcomer of the loading arm. That's what's happening. Let's pay a little bit of attention to that because there's a flat region here. What's the reason for that? It's a flat at 30. See, that's the length of that pipe. So the whole pipe becomes full of vapor when the valve closed. And this is completely undesirable. This is because LNG is very volatile. And that's the reason why it's so important to consider cavity forming. And so LNG is becoming more and more important as in the oil and gas industry. And it's absolutely crucial that you model the loading system. And a lot of LNG loading systems are being modeled using PIPENET. It's the same with the regasification and bunkering systems, because LNG loading systems are only with countries which produce LNG. But regasification systems and bunkering systems are all over the world. There are many, many systems. And it doesn't actually cost that much to go the extra mile and do the modeling of the system in order to eliminate the cavities being formed in the loading and unloading part of the system. So this model has uses in LNG loading, LNG regasification, and LNG bunkering system. They can all use such models. Okay, so let's consider a third case, which is where, see, we close that valve, but leave that 0.1. I kept it 0.1 rather than 0 because 0 is the vapor pressure of the LNG under the operating conditions. So I'm maintaining a slightly higher pressure because otherwise you'll have complications with the vapor formation constantly in the system. We need to avoid that. That's why I made it slightly bigger than 0 bar gauge. Okay, that's a third model. I said better, but not good design. My tea is getting very cold, so I'll just have a sip if you don't mind. Just for your information, some of you may have heard that we've got a heat wave in the UK. Yesterday, the maximum temperature was about 39. 39 maximum is what you would get in tropical countries. So it's been very, very hot here. So I've got lots of tea and glass of water and stuff like that in front of me now. Anyway, what's the difference? That's closing. That's closing. But that, it left its original value. In other words, the connection is to the top of the tank rather than on base. You see, the point about these cavities forming here is even if the cavity collapsing doesn't give a very, very high pressure, it's still problematic because you can get these oscillations in the cavity volume curve, which is something that you want to avoid. And also the cavity collapse could produce vibrations due to forces, hydraulic transient forces in the system. So that the cavity formation, our aim is to eliminate that, not only because the cavity collapse can give very high pressures, but also because it is something undesirable, because cavity collapse is always undesirable. So let's see what happens now. That's the loading arm. Goes to a high point. This is the cavity volume, or the length of the cavity. And then it comes down and stays at 80. It doesn't actually go to the 30. Why? It's simple, because you see, when this valve didn't close, there is no restriction downstream of this arm. So the liquid keeps on flowing, and it's flowing in and out of the system. That's why the cavity is oscillating. But if you close this valve at the same time as this one, albeit more slowly, this is closing more slowly, you can see, you will get a cavity forming here, but it will not fully develop because this valve has already started closing, which is restricting the flow out of the system. And certainly it'll stop the fluid flowing back from the tank. And that's why we're not getting those terrible oscillations. Nevertheless, it doesn't completely eliminate the problem because there is a certain amount of cavity that forms that gets trapped in the system. So it's better than leaving everything open downstream, but it's not a perfect solution. You can say that if, for example, the tank was empty, say there was an emergency and this valve closed for some reason when the tank was not full, even though you may have the connection at the lower end of the tank, it'll still have a small back pressure. And so that is, you could say, that is what we're modeling in this case. Anyway, that is how we can do this very useful study of the loading arm. And do remember, the applications are widespread. It's not, LNG is everywhere now. And it's this philosophy can be used in loading system, regasification or unloading system, and bunkering system. All of them can use this, and it doesn't cost extra, that much more, to go the extra mile and refine your design using this principle. Okay, so that's what loading system is about. So let's carry on. All these are described here. Here, we're considering a crude oil transfer line. This could also be an LNG. See, for example, this could be an FLNG, where you've got cargo tanks which have got LNG, and then you are loading a tanker from the FLNG, and you would have a loading system. But this is actually crude. It's an older system, so it's an FPSO rather than an FLNG, and so it's transferring crude. And that's a shuttle tanker, and this part here is the, up to here is the FPSO, and that's the offloading hose, which is flexible, and the tanker, shuttle tanker, starts from there. It's a very, very simple principle you can use for reducing the pressure surge, because you know that the offloading hose is a weak point in the system. And you know, it's surprising how nature works against us sometimes. In this case, that's about the worst point in the system from an environmental point of view as well, because if this brings a leak, it's going to go straight into the sea. And that's something we want to avoid. So the study that I'm talking about now is crucial, and it is very commonly done. Close that. So there's cargo tanks. I don't want to go into too much detail of how the system is operating. The traditional design would be, when the shuttle tank is full, you might simply close this valve here, or you might close it for some other reason. See, I'm considering the closure of that valve because I want to study cavitation, basically, and we can expect potentially cavity to form here when the valve closes. And we're looking for a simple solution. See, this is called an ESV valve, but it doesn't have to be. It could be any valve. I'm closing that valve. You can see that I'm not closing it as I would an emergency shutdown valve, and it's closing in 28 seconds. So I'm modeling that as an actuated valve closing. Okay. So let's look at let me zoom in so you can see the pipe labels. See, I've modeled the loading arm, the transfer line, the hose, in a very simple way. 3 sections, one going straight down, the horizontal part, and that's going up. Now, if you want to model the offloading hose as a catenary, you can actually model that as a number of pieces, okay? I'm taking a very simple approach here. Vertical going down, horizontal part, vertical going up. And that valve is closing. Although it's called an ESV, I'm operating it like an actuated valve closing. So let's run this and see. See, this design was actually done on behalf of the operator of the FPSO, and that's why they were considering the possibility of this valve closing. You know, you may actually have that valve closing, and that may not create cavitation here, I don't know, but this will almost certainly create cavitation in this part of the system. Here again, we're using the channel cavitation model. You know, the results are absolutely beautiful, I can tell you. The 39, 40, and 42. 39, 40, and 42. Make a note of that. Go to the graph viewer. "39" is this one here. Let's follow them in a sequence, 39, 42, and 40. You can see cavity forming. I don't have to show this, but this horizontal section here means that vertical section is completely full of vapor. Then look at 42. See, when that's completely full of vapor, we get a small vapor pocket forming there. But you see, what this means, it doesn't mean there is no problem there. What it means, see, there is, when the vapor actually forms in this section here, let me zoom in again. When the vapor forms here, it doesn't instantly become vapor here. The vapor actually starts moving, but what happens is this remains full of liquid for a while, and that actually becomes vapor. It all depends on the pressure, you know, because this is at a lower point. The pressure here will become less than the vapor pressure first, because it's got an elevation change before this becomes below vapor pressure, and that's what we're seeing here. Then, of course, it gets a big vapor pocket. And let's look at 40, which is the rising section. See that starts getting vapor around the same time as this small peak here. Nevertheless, you know, the important thing here is that PIPENET is actually modeling quite beautifully how the vapor column keeps moving, or rather the liquid column here keeps moving between these three pipes. That's what that is showing. You know, you do have a look at it in your leisure. You'll find that we haven't got time to go through that in so much detail. You can see that the liquid column is really beautiful when you look at it, how it keeps moving back and forth along this offloading hose. Anyway, that's not the main thing we're looking at. The main thing we want to see is how can we eliminate it. It's a very, very simple approach. As I said, I'm modeling this as an actuated valve for convenience. I'm going to say that, you know, this communication between the operators in the FPSO and the shuttle tanker. So these two valves are closed at the same time as that valve there. See, the cavity forms here because if you shut this valve on its own, there's a depression in the pressure here. But if you close these two valves, or at least one of them, then that will reduce the depression in the pressure in this part of the system. That is the logic behind it. Let's see if it works. See, once again, it's a very, very simple approach. It doesn't involve great modifications to the system. It is an operational procedure that the shuttle tanker and the FPSO operators will have to communicate with each other and make sure that they close at the same time. If, of course, if it works. Its maximum pressure seems quite reasonable. And let's look at those three sections again. '39, which is the first one. Wow, brilliant. There's no cavity forming at all. For good measure, let's look at 42. Zero, wow. And then look at 40. That's also zero. So there is no cavity forming in the flexible connector, the offloading hose. See, this is the beauty of engineering. We found a very, very simple way of overcoming the cavitation and the problem that could potentially cause in the offloading hose by simple operating procedure. You know, I would highly recommend this option. So time is almost up. So let's just look at one more system, which is a water injection system. I will just run one of them because I don't think we'll have time to run all of them. Now I will run this for a specific reason to illustrate a point. You see, basically, this water injection system, this is the, these are the lift pumps, and these are the water injection pumps here, and that is the well. With this actually going all the way to the well, you can see the length is 3,000. The net elevation changes 2 kilometers. So this is actually the well that's being modeled here. We also have a control loop. And what we are modeling here, this pump here, we're using the inertial pump model here. That pump is shut down. And the control system is going to model the shutdown of these two pumps. See, that's a switch. More importantly, it's modeling the emergency shutdown valve here. And both of them, I believe, are closing. Yeah. See, what we want to see here, not simply what's going on in the system. What's most interesting in this simulation is what's happening at the injection point. What can happen sometimes is that because the pipes are elastic, when you close an ESD valve here, the pipe can contract because we're working at a high pressure, and you can get a flow back into the well. And that's highly undesirable because when it flows back, it'll undoubtedly bring sand back into the system. And that is something we should avoid. And because of lack of time, I'll simply show the effect of this. See this pump there, water injection pump is stopped. That's running. That's running. But the ESD valve is closing. See, what we want to see is what's happening to the flow rate there. I believe this. You see, look. We can plot the zero line there. So it's actually substantial amount of water is actually flowing back into the well. We don't want that. We need to avoid that. Okay. And then, because of the nature of water hammer, this is a flow rate. Don't forget, it's not the pressure; it's a flow rate. It actually indicates the flow in and out of the well. And that's what we're getting here. Anyway, I've said everything I want to say. There's more I had prepared by way of presentation, but we don't have time, unfortunately. There are many scenarios for water injection systems which are very interesting. Some are concerned with the control systems and things like that. Just one thing I'd like to say is that we have the PowerPoint presentations of the different scenarios and things like that. We'd be very happy to send the PowerPoint presentations to any of the attendees on request. And if you are a valid customer of PIPENET with a license, then we can also send you the data files if you are interested in that and if it will be useful to you. Please contact Victoria. She's the main person, the main contact from that point of view. And depending on where you're located, either we will send you the information directly or through a local person who works with Sunrise. Okay, and thank you very much for being here. And again, this session is being recorded and Victoria will circulate them. And it's the same for training certificates. And Victoria, can you spend just one moment explaining, what you would do after this?
Okay, Dr. Sebastian, thank you very much for delivering the presentation. So afterwards, if you would like to receive a certificate of attendance, please send me an email and we will be happy to provide the certificate. I will also send the video recordings to everyone who participated today. And if you would like to get the materials that Dr. Sebastian mentioned now, please also mention that in your email and we will be happy to share. Apart from that, please follow our announcements because we are planning to have more webinars later this year, maybe in October. So please follow our announcements, emails from me or on our behalf, and we look forward to seeing you again. Before we leave, I would like to ask Dr. Lajin and Ms. Chalvi whether they managed to answer the questions in the chat. Chalvi, Lajin?
Yes, Victoria, there are a few questions which will be answered privately because of the nature of the questions, but otherwise it's done.
Okay, thank you very much. Lajin?
Yes.
You answered the questions. Okay,
Yes.
Thank you very much. So I would like to repeat, if you have any more questions, if you think of any questions tomorrow or any other day, please feel free to write to us and we will be happy to answer your questions. So today's session is over. Thank you again for being with us and we look forward to seeing you in the future. Have a good day, have a good evening, and bye-bye.
Thank you very much for being here. Thank you. We'd love to see your customers. Wonderful to see you. Thank you very much. Bye-bye.